Good morning. Today we will be talking about position sensors. This presentation is for 2 lectures, so this week and next week, since position sensors are quite important for a mechanical engineer, so we'll be talking about them for 2 lectures. We'll be talking about different kinds of position sensors, and we'll be talking about sensors for linear and angular displacement. Today we'll be mostly talking about sensors for linear displacement. At the very end we'll start angular. There are many types of position sensors. Regarding of what properties does this sensor have, we'll be talking about absolute and relative sensors. What's the difference? The difference is in the behavior of the sensor after power up, after you turn the application on. So there is a difference in behavior between absolute and relative sensors. Absolute sensors, they give you directly the information about the position when you turn the application on. You don't need to do any movement to some reference point. Relative sensors, on the other hand, they require that initially you make a movement to some specific position, to some known position that is defined, for example, by an AND switch. There are applications where you don't care if this is a relative sensor or an absolute sensor. And there are many applications where you need either an absolute or a relative sensor. An example where you need an absolute sensor is, for example, control of electric machines. There are special algorithms for electric machines and their control if you want to control the motion of an electric motor. And electric motors are used, for example, to drive trains, trams, and so on. So if you would use a position sensor in this kind of application, and you really use this sensor, the sensor is sensing the position of the shaft of the motor in order for the algorithm to work. And there's no way you can make a reference movement. So there's no way you can move the train forward and backward a little bit. So you need an absolute sensor for this. So absolute sensors are good for applications where you cannot do this reference movement. You need directly the correct position information after you start the machine. On the other hand, there are applications like CNC machines, for example, where you require a high accuracy. It means you need a really high resolution for the sensor. And this is the task typically done by relative sensors. So relative sensors, when you start the application, you don't know exactly at what position you are. You make a reference movement to some end switch until it hits the end switch, then you know this is my 0 position. And then relative sensors, they count pulses from this relative position. So if you start at an arbitrary position, you can just say, the motion was 100,000 pulses in this direction or in the other direction. And you know how much is a single step in the relative sensor. So relative sensors, they require this reference motion. They require end switches at some defined positions. But on the other hand, relative sensors are typically much more accurate than absolute sensors. So there is a trade-off between resolution, which is greater for relative sensors, and between the necessity to have this reference motion at the beginning. So for example, CNC machines, they typically use relative sensors. When you start the machine, it's moving to some 0 position, it hits an end switch. And then from this point on, it counts the pulses and it just knows that it's moving to the left or right and how many steps did it make. An example from home appliances, you can find relative sensors, for example, in inkjet printers. When you start the inkjet printer, the printer head moves to a reference position. It sets 0 by there is an end switch, either a mechanical or an optical, and then there is a relative sensor that counts the pulses. If you move the head manually, then the printer needs to reset to this reference position. And next week, when we'll be talking about this kind of sensor, I'll bring the sensor from this printer. So that's one category, absolute and relative sensor. Today, we'll be talking only about absolute sensors, and relative sensors will be next week. Then we can have position sensors, analog or digital. The difference is in the function, how is the sensor working. So some sensors will be analog in nature, so it means they can give you a virtually unlimited number of positions. Some sensors will be digital in its nature, and they will have a limited resolution. This is not related with the output signal of the sensor. Even if you have an analog output signal, the sensor can be digital. Even if you have a digital sensor, the output can be analog. It can be current, voltage, or something else. So this is speaking about the principle of the sensor itself, not about the output signal. Then we will have two different categories. We'll have continuous sensors and proximity sensors. Continuous sensors are good if you want to measure, for example, a distance between the sensor and the object, and you want to know how far the object is. Position sensors that are continuous are used in many applications, but they are typically more expensive. There are applications where you just want to know the object is there or the object is not there. Example is if you have a conveyor belt, you have some products on the conveyor belt and you want to pack those products in some boxes, then you just want to know the object is on the conveyor belt or it's not there. So you will use a proximity sensor, which should be less expensive. The output of a proximity sensor is 0 or 1, yes or no. So it's telling you the object is present or the object is not present. It's not telling you how far the object is from the sensor. So for applications like conveyor belts, packing of objects, it's sufficient. You just see, okay, the object is there, I'll pack it. For applications where you need a continuous reading, you will need to use continuous sensors. Today, we'll be talking only about continuous sensors, and proximity sensors will be at the end of the next lecture, next week. Position sensors can use many physical principles how to detect the position of something. We'll be talking about sensors that use electrical resistance, inductance, capacitance, eventually magnetic properties like eddy currents, and we'll use also optical sensors. So those are the basic principles, those are the most common ones, but there are many others which you can use for specific applications. We will start with resistive sensors. So resistive sensors will change resistivity of something in the sensor, and we'll read either the resistivity or we will read the voltage that will eventually come out from this sensor. So I have to wait for my computer. It's doing something and it seems to be stuck. So resistive sensors, they will work by changing resistivity of a variable resistor, typically. So the sensor itself will look like this. It will be a variable resistor, and we will have 3 terminals on this variable resistor, and we will read the output voltage that is between the movable part, between the slider, and between one of the fixed terminals. So this will be output voltage. Let's call that V2. And here we will have input voltage. Let's call that V1. Since we will be changing the position, then here the position of the slider, let's call that X, is what we want to measure. And we will be looking for the output voltage as a function of X, as a function of the position. Here we will define the resistance of the sensor. Let's say it will be R0. It can be a few kilo ohms typically. And this R0 is the whole resistance between this terminal and between this terminal. We could measure directly the resistance, but typically we measure the voltage out on the output V2. And we measure that with a voltmeter that has some internal resistance. Let's call that RL. I'll try to restart my computer. So here the input voltage will influence also the output voltage. The bigger the input voltage, the bigger the output voltage. We could derive an equation for this V2. In order to do this, we have to split this R0 into two parts. I will call this R2, and R2 is the section under the movable part, and R1 is the section above the movable part. So now we can redraw this circuit in the following way. This will be R1 and R2, and here we have the input voltage V1, and here we have the output terminals V2, and there is a resistor that represents the voltmeter, the load. So if I write the equation for V2, it will be looking like this. It will be RL in parallel to R2 over R. That's not correct. Hold on. So I need to make it bigger. So it will be RL in parallel to R2, and here it's RL in parallel to R2 plus R1 times V1. So now if we substitute this for the parallel formula, we will see that it's RL times R2 over RL plus R2, and here we have RL R2 over RL R. So here we have R2, RL, that's the load resistance, and this is R1, that's the resistor above the movable part. So from this equation, we see that the actual voltage depends on many variables. It depends on the power supply voltage. So if the power supply voltage will change, we will have a different voltage on the output, even if the position X is the same. And R2 and R1 are functions of position X. So now we can say that R1 is dependent on position X. And let's define it in this way, so that when it will be all the way down, R2 will be 0, and when it will be all the way up, the R2 will be R0 and R1 will be 0. So here we can write that R2 equals X and times R0, and R1 equals 1 minus X times R0. In the equation, we also see that the position that we read, the output voltage here, will depend also on the load resistor. So it will depend also on the properties of the voltmeter that we have here. So we'll need to cover this as well. And I'll try to open the equations. So we will have this equation, and this equation. From this, we will see that the output voltage will be a nonlinear function, because it will depend also on the load resistor, and there will be a specific value for the voltage of on the resistor, so that we can read the voltage directly on the output. So this is the equation that I just wrote on the blackboard. So that's the voltage on the output of the voltage divider. It's just a different form. And here you see we have the definition for R2 as a function of X times R0, and R1 as a definition of 1 minus X times R0. The ratio K will represent us the resistance of the load versus the resistance of the sensor. So the resistance of the load, I call that RL, and the resistance of the sensor itself is R0. To give you values, the sensor that I have here, I will show you in a few minutes, has R0 of 5 kilo ohms, and this will be the resistance of the voltmeter. And when the resistance of the voltmeter is small, it's getting closer to the resistance of the sensor, we will see that it will influence the steady state characteristic. So it is the property of this kind of resistive sensor that the type of steady state characteristic depends on the voltmeter type that I use it to measure. The ideal ratio for K will go to infinity, because if we substitute this, and this into this equation, we will see that it will get quite complicated, but here is the result. Here, this is K, that's the ratio of the resistors, X is position. And from this equation we can see that this relation is nonlinear. And it will be linear only if I will have a very high value of K, and very high value of K means I have a very high input resistance of the voltmeter. So the goal for all experiments with resistive sensors is to use a voltmeter which has a much higher input resistance than the resistance of the sensor. So if, for example, we'll use in the lab a sensor with just 5 kilo ohms, then you should use K higher than 100. So it will be above 500 kilo ohms. So if you use a digital voltmeter, then that's not a problem at all. you have a linear relation between position and output voltage that you measure. But if you use, for some reason, an analog voltmeter with low input resistance, then it will have an effect on the steady state characteristic. I have later some charts where you will see what happens. Moreover, here, since the output voltage is a function of K, it also means that if for some reason I will change the load resistance, for example by changing the range in the voltmeter, then it will have an effect on the voltage that I measure. So for this kind of sensor, you should never switch ranges if you are using an analog voltmeter, because then you will see that directly on the steady state characteristic. So the ideal ratio for K for resistive sensor is very high value of K. The higher, the better. Typically, if it's above 100, then it's fine. Digital voltmeters, they have a high input resistance. So there is no problem at all with digital voltmeters for this sensor. Digital voltmeters, they usually have at the input resistance higher than 10 megaohms. So if I take a sensor 5 kilo ohms and 10 megaohms, then that's definitely higher than 100 times, bigger than 100 times. And then with digital voltmeters, we don't have any trouble. We can also use this equation to calculate absolute and relative error. We will do this by comparing the value that is coming from this equation, which takes into consideration the value of K, and this equation which considers that the dependence is linear. And we will say, okay, this works fine for a voltmeter with a very high input resistance. But what happens if I don't have this kind of input resistance? If I really have some ratio K, and we'll look for the difference. So we know that the relative error is the difference between the measured value, measured voltage, and the correct value. It's in percent, so that's times 100. So here, this is the equation for relative error, and this is the ideal voltage, so X times V, and here we have the real voltage that is coming from this equation. And when you derive that, you will see two interesting things. One is that the relative error is always negative. It means that you measure always a smaller voltage than you have in reality in the circuit. And we can also see that the relative error will be 0 if RL is going to infinity. In other words, if I use a digital voltmeter which has a very high input resistance, I'm increasing the value of K, which is here, and K is increasing, and therefore here we have a larger and larger number, and if K would be infinite, then relative error would be 0. So this is the reason why we are trying to increase as much as we can the input resistance of the voltmeter. On the other hand, if you increase this input resistance, you can increase that today without any problem to, let's say, 10 gigaohms, but then you have a very sensitive circuit for electromagnetic interference. So that's a trade-off between interference and relative error in this case. So the relative error is always negative. How about the position of maximum relative and absolute error? If I would plot you this function V2 as a function of x, we will see that for the sensor x from 0 to 1, and here from 0 to 1 will be V2 over V1. The ideal sensor would have a linear characteristic. So this is the V2 is x times V1. And this is the ideal curve for k going to infinity. We will now look for the chart for the relative and absolute error. And we will see that there is one specific position at which the absolute error is the biggest, and there will be also a specific position where the relative error will be the biggest. Let's start with the relative error. How do you look for the position where you have the biggest difference? Well, you make a partial derivative. So I will make a partial derivative of x, and I will set that to 0. And I will look for a value of x that fulfills this equation. So this is the equation that we already know for the relative error. Now if you make a partial derivative of this over x and look for this equation equal to 0, you'll find out that this equation is fulfilled only if you have a position of x equal to 1/2. So this means that regardless of the value of k that you have, the maximum relative error is always in the middle. So if we will plot the dependence for another value of k, so this is k, let's say, smaller than infinity, it will look like this. From the analysis, we know that the voltage that we measure will always be smaller than the correct one, which is this one. And from this equation, we know that the maximum relative error will be in the middle. So here, there will be always the maximum error. And this does not depend on the resistance of the sensor, and it does not depend on the load resistance. So always here you have a maximum relative error. The actual value of relative error, of course, depends on the value of k. So here we will have a difference in relative error if k is getting smaller and smaller, but the position will still be the same. We will use the same procedure for maximum absolute error. So we'll have the voltage here. That's the voltage V2 coming from the sensor, and this is the voltage that corresponds to the linear response in the case where k is going to infinity. We can make again a partial derivative here, set it to 0, and we'll see that the position of maximum absolute error is roughly 0.7. I say roughly because this position x now will depend on the value of k. So for example, for k equals to 1, the maximum absolute error is at position 0.69, which is somewhere around here. So this is the maximum absolute error. But the position is changing slightly with the value of k. Only slightly. Let's say from 0.69 to 0.7, but it's changing a little bit. So the maximum relative error is fixed, and the absolute relative error is moving slightly, but it's always somewhere around here at 2/3 of the full scale. To show you some measured data, here is how it looks like. So those are data for a sensor that's similar to the one So here on the x-axis there is position between 0 and 1, so between minimal and maximal position, so full scale. Here we have the ratio between voltage V2 and voltage V1, so between 0 and 1. The blue line is for k going to infinity, so that's the linear response. This is what you will have if you have a voltmeter with a high input resistance. Here, this magenta line is when you have k equal to 1. So it means you have the same resistance in the sensor and the same resistance in the voltmeter. So for example, we will have 5 kilo ohm sensor and 5 kilo ohms voltmeter. So here then in fact this is 5 kilo ohms and this is 5 kilo ohms as well. And you see that it has a huge effect on the voltage that you measure. So we already know that the maximum relative error is in the middle, always here. So this is the biggest relative error. The maximum absolute error is somewhere around 0.7 of the full scale. But there are also two other interesting points. At position 0, you see that relative and absolute error is 0. So here we are measuring accurately because we measure 0 voltage. But the same happens also at full scale over there. So here at this point and at this point you always measure with 0 relative and absolute error. But in the middle you have the highest relative error. So now let's take a look on the materials that are used in resistive sensors. A resistive sensor is nothing else than a variable resistor in principle. So the resistive track can be made from a wire, it can be made from a metallized layer and other materials as well. The oldest sensors and oldest variable resistors, they were wire wound. So it was a coil of wire wound on some core. And you have a problem with low resolution. Imagine we have a wire, this wire has some diameter, and we are basically switching between those wires. So a wire wound resistor used as a sensor has a lower resolution compared to the other principles. But on the other hand, it's robust. It's good for environments where you have vibrations, where you have humidity and so on. The second possibility is to create a metallized layer. So it's a basic material where you have a metallized layer on top of it, and the slider here, this is moving on the layer up and down, left and right. This has a higher resolution than the wire wound sensors, but it's limited by the, let's say, durability of the material itself. So metallized sensors are prone to damage from vibrations, and they can be damaged by motion that is happening at one position. What I mean by that, let's imagine here we have this piece of material, then there is this metallized layer, and on top of it we have the slider that is moving left and right. So if I move the slider in full scale, then it has a defined lifetime for some specific number of cycles. But for example, if there will be vibrations superimposed on some constant positions, then it will damage this layer at one spot, and then you will have a, let's call it, blind spot, and it will be damaged at this point. So it will work in the whole range, but at one point you will have a discontinuity. So disadvantage by using other materials. The other materials that you see here are a selection of 3 that are used for variable resistors. The carbon is the worst. Carbon, you know, carbon is very soft, and carbon will be very prone to this damage. So carbon variable resistors are good for low-cost applications, such as volume control, for example. You can use a variable resistor to control volume of an audio signal in an amplifier. But they are not good for industrial applications where you will have vibrations. In industrial sensors, either a layer of conductive plastic or a cermet is used. Conductive plastic, I have some example on the next slide. The cermet material is a composite material from a metal and from ceramics. So it's kind of an alloy. And the metal provides conductivity here. It also provides the plastic behavior. And ceramics provides stiffness. So then the whole piece of material is good also in environments where you have vibrations. So we'll be talking only about conductive plastic and about cermet materials for industrial sensors. The cermet material has also other advantages. It can work in high temperature applications, and it has a quite good linearity in the whole range. So here you have examples of numbers from data sheets for different sensors that are using this cermet material. So now, how does it look like? What's inside? This is an example of a sensor from conductive plastic. So this is the sensing element itself. So here, that's the basic material, and here those 2 black strips are the conductive plastic, and then the slider is moving on top of this plastic layer. So it's sensing the changes in electrical resistance. The sensor from the outside looks like this. So here you attach this sensor to a frame, to the part that's not moving in your application, and you attach this slider to some part in your application that's moving. I have here an example. So this is a position sensor, but you will use that in the labs. So that's the sensor itself. It's attached to a frame, and this is the slider that is attached to some part that I want to sense the position. The output is 3 terminals, so I will connect that to a power supply and measure voltage. And this specific sensor has 5 kilo ohms resistance. You can see the ranges. That's only for this type of sensor and for this manufacturer. But just to give you an idea, from 25 millimeters to 1 meter. If you have different type sensor, I believe this one is like 30 centimeters only. It has a high accuracy, so you can see plus minus 1%. It can be also more accurate. You see here sensor type linear conductive plastic. So conductive plastic is inside of this material. They say essentially infinite resolution. Yes, the layer itself has an infinite resolution, but then it always depends on the resolution of your measurement instrument. So here you are not limited by the sensor, but you are limited by the accuracy of the voltmeter that you use. If you use a less accurate voltmeter, you'll have a less accurate reading. Another example of a position sensor based on resistivity changes is this one. So from the outside it looks virtually identical. Again, this is the frame, and this is the slider. It moves someplace. Here we can see also the voltages and currents that are allowed for this sensor. So if we have this sensor connected to a power supply, V1, we could, in theory, increase the output signal by increasing the input voltage. But we are also limited in the current that can flow through this sensor. So typically, this maximum current is limited to a value of roughly 100 milliamperes because we want to prevent heat in the sensor itself. So here you see the maximum allowed current through the sensor is 100 milliamperes, and therefore the maximum voltage is roughly 30 volts. That's also for security reasons. We don't typically want higher voltages than roughly 50 volts. So you cannot connect an arbitrary voltage to the sensor. You are limited by the current that can flow through it. So those are linear sensors for linear position. But the same thing will work also if you make the track circular, and you can have variable resistors, sensors that are good for angular motion. Of course, you can transfer between linear motion and angular motion with a gearbox, for example. But if you directly know that you will use an angular sensor in applications for angular motion, then you don't need any gearbox at all. The properties of angular sensors are the same like for linear sensors. So you again need to watch for maximum voltage, maximum current, and it has exactly the same properties like the linear one. It means a specific position for relative error, absolute error, and there will be always a difference between the measured signal and between the real voltage that I have from the sensor. Any questions related to resistive sensors? Okay, good. So now we'll be talking about inductive sensors. So inductive sensors, they will use the changes of inductivity of a coil to detect position. So resistive sensors were powered by DC voltage, but inductive sensors, since we are exploiting changes of inductivity, they need to be powered by AC voltage. So here you will need an AC power supply, and the AC power supply is in some cases built in to the sensor. So the sensor is powered by DC, but there is an integrated electronic circuit that creates AC voltage from it, powers the electronics, and then eventually converts this to a current or output signal. I will be talking only about one inductive sensor, about the most common one, and this is called an LVDT. LVDT stands for a linear variable differential transformer. And LVDTs are very robust, and they are very accurate. So they will be used in applications where you need to sense position with a resolution of some micrometers, for example. The name differential transformer implies that it will be some kind of transformer. So inside of this sensor, we have three windings. We have a primary winding and two secondary windings. The primary winding is powered by AC voltage from the power supply. It has some inductivity, L1, which is constant, and there will be some current flowing through this primary winding. Let's call that I. This primary winding will create a magnetic field around it, and this magnetic field will pass through the core into the secondary winding 1 and into this secondary winding 2. The core is made from a ferromagnetic material, and if it is in the middle, it means that I will have the same voltage in this winding and the same voltage in this winding, because I will have the same coupling between those two windings and between those two windings. The output voltage in those secondary windings is also AC. Now if I move the core, in my case up and down, let's move it down first, I will decrease the induced voltage in this winding, and I will increase the voltage in this winding, because the magnetic flux will go through the core into this winding and not into this winding. If I move the core up, there will be higher voltage in this winding and smaller voltage in this winding. So the voltage that I measure on the output of the secondary windings will be a function of the core position. So the transformer, the sensor itself, is attached to a frame, and the core is attached to the part that you want to measure. So this is what's sensing the position. I could directly measure the output voltages from this winding and from this winding. This is done internally in the electronic circuit, but I could also connect them in this way. You see that now the two windings are connected in series, and they are connected in such a way that they have different polarity. Here, if the core is in the middle, I have this terminal going out, and this terminal is connected to this terminal. So it's kind of two batteries connected in series. The output voltage when the core is in the middle will be almost zero. So when the core is in the central position, I will have a very small voltage at the output. And then when the core is moving up and down, I will be able to measure some voltage. The steady state characteristic typically looks like this. So here you have position. Now the boundaries are minus x and plus x. So the sensor measures in both directions, and the voltage at the output is the same. When you are in the central position, due to straight fluxes in the core, the voltage is not zero. So here we have a very small voltage at the zero position. Then we have a linear section and linear section here as well. So this is where the sensor will be used. We will use it somewhere around here where the voltage is linear. And this flat section here and here is where the core is too far out from the transformer, so there is no reaction on the input position. So here we cannot use the sensor anymore, because even if I change the position, I don't see any response on the voltage. So we will use the voltage here on this, the sensor will use it here at this section or in this section. I have a video here that is showing what's happening inside of the sensor. So let's take a look on it. So that's a demo of applications where you may find LVDTs and what's inside of them. So here, this is the stator. Well, let's go to some pictures. So this is the arrangement of the sensor. Here you see that's at one position. Let me. Oh, it's going too fast. Let me stop it. So when the core is in the central position, we have the same magnetic flux here and here in those two secondary windings. And when we add the voltages together, it is zero almost. When we have a maximum position to the left, then the maximum coupling happens between those two windings. So there is a maximum voltage here and minimum voltage here. And the same happens here at this position, top right. We have maximum voltage from this winding and minimum voltage from that winding. If you look on the oscilloscope, it is a sinusoidal voltage because it's AC voltage. The typical frequencies are a few kilohertz. So we are not using directly the voltage from the mains, 50 or 60 hertz, but we are powering that with some higher frequency. And if you move it to the left and right, you will see that the voltage is decreasing and increasing as a function of position. Typical application, you have a ball screw, for example, and you want to sense the position of this assembly. So you mount the movable part to let's say the part of the machine. So you see here Lvdt and the sensor here. This is a motor, and if you want to sense the position of the ball screw, you need a sensor for that. So that's an application where you have a motor that and a control system that requires a feedback. So you see it here. What happens also with the voltage at the secondary winding when this is moving? You see this is the sensor, this is the motor, and then the controller senses the position and uses feedback control to accurately check the position. So there are some more videos. Let's see this one. This is basically the same. Let me just show you one picture here. So this is the sensor itself, the principle. So the primary winding, secondary winding, and another secondary winding. And this is the core inside of the sensor. And when the core is moving in and out, the coupling is changing, and we are able to measure the changes in amplitude in this sensor. Now let's take a look on the characteristic of an Lvdt. Here you can see from this steady state characteristic that either we could use the sensor only in this area or only in this area. We could, however, also combine this information with the phase shift of the voltage, and we could use it from this position all the way to this position if the electronic circuit is, let's say, smart enough. This is another example of a steady state characteristic. So for the null position, we have non-zero voltage. This is one linear section, another linear section. If you watch also for the phase angle between the voltages at the secondary winding, so between this voltage and between this voltage, the phase shift will also change, and we can detect that with some kind of circuit. So here you see the phase shift. Here the phase shift is either positive or negative, and if we combine all this together, then we can have a linear response from minus x to plus x. So if we would use the sensor directly, we measure voltages inside of an industrial sensor. This is combining also the phase shift information, and then you have a full range from minus something to plus something. Here is the composition of an Lvdt. This is the iron core that you connect to the movable part. This is the primary winding, and this are the secondary windings. So from the outside, it then looks like a pipe, and it looks like this. So this is an Lvdt. So the secondary winding is all here, and there's one secondary winding here and secondary winding here as well. Here is the movable part. So you connect this to a frame, and you connect this to an object, and then this gives you the position. This sensor has current output from 4 to 20 milliamperes. So although internally the signal is voltage, it is converted to current. So there is an additional electronic circuit and operating amplifier that creates current from voltage. What can we expect? LVDTs are very robust sensors. The only movable part is the iron core. So LVDTs can work in applications where you have vibrations, for example. The friction is a function only of the mechanical properties of the slider of the core itself. So the friction can be very low. It means also the force acting on the object can be very low. And LVDTs achieve high precision, high resolution. Here you have some examples of LVDTs. The size is a function of what you require. So LVDTs can be small and accurate, but can be also large and accurate as well. I have here a few examples of LVDTs. So those are LVDTs that are mechanically smaller range, but higher accuracy. So you see it's the same principle. Here, this can move, and that's the core that's moving. And here we have the windings inside of this pipe. We already have used this sensor. In what lab class did we use this kind of sensor? In the force lab, we use this LVDT to measure the bending of the beam. So this was used as a position sensor. There are other LVDTs here as well. As I said, it depends only on the range that you require. The resolution that you can achieve with an LVDT is quite good. So LVDTs can be used to measure within few micrometers, at least the smaller ones with smaller ranges. I have selected only 2 applications just to demonstrate how this is used. LVDTs are used in aerospace, and one application where this is used is to sense the position of a thrust reverser in the airplane. What is a thrust reverser? What is it good for? Or in other words, how does an airplane brake when it lands? So there is a mechanism that's called a thrust reverser. I have a video. Let me find it. So some of you have arrived by the airplane, and when the airplane lands, then in order to brake the airplane, you need to reverse the thrust of the engine. So there's no way that you reverse the rotation of the engine, but there is a mechanism that helps you to reverse part of the thrust against the motion of the airplane and brake it. When the airplane lands, you will see that here a slit will open, and that's what is redirecting the thrust against that. Later have some other video as well. And this is how the airplane brakes. So now this is sensed, the position of this is sensed by an Lvdt. And you see the thrust of the airplane is going against the motion, where they are using Lvdts to sense the position of this mechanism. Another video, hopefully. So again, some trouble with the computer, so probably no video. I wanted to show you another video. So I think this is the one. So this shows you the thrust reverser in action, and hold on, I'll just fast forward that. So now this is the engine operating in normal mode, and now this will the mechanism will close and will like this. See, it will block the thrust going backwards and now redirect a little bit of it forward. So this helps you to stop the airplane. Another application for a mechanical engineer, if you produce thin sheets of material like metal or plastic, this is typically done by rolling. So you have two rollers, and you need to very accurately control the gap between those rollers, so we have the desired thickness of the product. So here you see the two rollers and the product, the foil, and the distance between the two rollers is measured by an Lvdt, because it's very accurate. It can have a resolution of few micrometers, and it's very robust. There is no problem with heat, with vibrations. So you see, Lvdts are used, for example, in those applications. Okay, and we will finish today with another sensor that is also based on changes of inductivity, but this sensor will be good for angular motion. So Lvdt is a sensor for linear displacement, but this sensor, that will be called a resolver, is a sensor specifically designed for angular motion. The composition of a resolver is very similar to an Lvdt. It's also working like a transformer. So we'll have one primary winding and two secondary windings. The primary winding, in case of a resolver, is on the rotor. It's powered by AC voltage, so this needs to be AC. And since this is on the rotor, you will need a mechanism to transfer the signal from the stator, from the power supply, into the rotor. So there is another transformer that is not shown here in this picture, since it's not important for the principle of the sensor, but it needs to be there anyway. The rotor position, let's call it alpha, is what you want to measure. So the resolver is a typical sensor used in electric machines, electric motors, and you want to sense accurately the position of the shaft of the rotor, because you want to control that, because you want to control torque, you want to control speed, and so on. So we create an AC magnetic field in this primary winding that is on the rotor. Now we have two stator windings, one here and one here. There's two stator windings are aligned with the angle of 90 degrees. So here we have one winding over there. If alpha would be in this direction, then I would have a direct coupling between the rotor and between the stator, and the stator in this position would be perpendicular to the rotor position. We will measure the output voltages from the two stator windings, here and here. And obviously, there will be a dependence between the amplitude of the voltages and between the angle alpha. For the input voltage, we can write that this is a harmonic function. It's a sinusoidal dependence. So the power supply voltage is some amplitude, let's call that Vmax, times sinus of omega t, which is the sinusoidal function. The typical frequency that is used for resolvers is somewhere between 2 and 10 kilohertz. So we are again not using AC 50 Hz or AC 60 Hz. We are using higher frequencies simply because if you use higher frequencies, the machine will become smaller. So you need less iron for higher frequencies, and we are not transferring any power here. So we are using these high frequencies, and the sensor then is small. The stator voltage will be derived from the rotor voltage. So the output voltage amplitude will depend on the input voltage amplitude. So this is coming from the input voltage here. And this sinus or cosinus depends on the position. So the output voltage on both windings will be a function of alpha, of the angle. But we need to measure both, because if we would look only on one of them, we would not be able to measure within one entire revolution. You will see that on the next charts. So on one winding, the voltage will be a cosinus function, and on the other winding, the voltage will be a sinus function. Now, let's take a look at the resolver signals for some positions. Here at this chart, this is an oscilloscope record if the position is fixed at angle 0 degrees. So this black sinusoidal is the power supply voltage. This is what you have on the rotor. So it's a sinusoidal voltage. And since now alpha is 0, then I will have one winding with 0 voltage. Which one? If you look on those equations, and if alpha is 0, then this term is 0, and then this voltage will be 0. And here, cosinus of 0 is 1, so I will have a maximum voltage on the second winding. So here we see that the yellow voltage, here the yellow curve, is 0 voltage, so that corresponds to the sinusoidal winding, to this one. And the cosinus winding has a maximum amplitude. So the sensor gives you two voltages, and you are looking for amplitudes. So here we have a maximum amplitude of this winding and a minimal amplitude of the other winding. Now if I rotate the rotor by 90 degrees, I will have directly the opposite. I will have 0 voltage on the cosinus winding, so now it is 0, and I will have a maximum voltage on the sine winding. So this is for position 0 and position 90 degrees. So I can plot now the dependence of the amplitude on this winding and this winding as a function of position. And we will see, it's also visible from the equations, that for one winding it will be a sine dependence, and for the other winding it will be a cosine dependence. So now if I would just use one winding, I could use the sensor not in the entire revolution, but only in a limited range. Imagine for some reason I would use just the sine winding, and I would measure just the voltage. So by measuring just the voltage, let's say I am able to measure in 1/4 of the the range. So let's say from 0 to 90 degrees. But here, if I measure, for example, this voltage, I have this point and I have this point. So I can't tell if I'm in this half or if I'm in this half. So for this reason, we need to combine those two signals together, and we need to add the second winding, the cosine winding, also in the equation. So now it's easy. Let's say I measure the two voltages. So let's say I pick this value, for example. So now this will give me this voltage or this voltage. But by looking at the value of the cosine, I can say, okay, it's here, and I am at some position, or it's here in this negative part, and I have a different position. So by combining the sine and cosine voltages, I can get the position information between 0 and 360 degrees. So a resolver is an absolute sensor within one revolution. If you would like to use it in more revolutions, you need to count the revolutions in a counter, for example. So within the range of one revolution, a resolver is an absolute sensor. But if you want to use it in high range, then it's a relative sensor. The typical application of a resolver is electric machines. You want to control the position of a shaft accurately. You want a resolution of, let's say, 4,000 positions per one revolution. And this is where a resolver is used. I have here an example of a resolver. This is the fixture that you will use on the lab class, and the resolver is here. So it's this silver cylinder that is sticking a little bit out from this plastic. Inside is those two pieces. Inside of a resolver, we have a rotor. So this rotor is on the shaft of the electric machine, and this is the stator that is at the frame. So as I said, typical example is electric machines. Resolvers are used in trains, in trams, and they are sensing the position of the wheels. And then the position is used to allow feedback control and allow torque and speed control of the train or tram. This is, by the way, also called Pancake Resolver. I don't know why, but it's a funny name, but they call it also Pancake Resolver. You can get also a resolver that looks like this. So this is an integrated resolver. So the rotor is then connected through a coupling to the shaft that you want to measure, and this is the stator itself. Some questions?